this video is about when the Lac Operon is actually going to be producing the gene product that is beta-galactosidase, or B-galactosidase. And when it is not going to be producing beta-galactosidase. And if you haven't already watched the first video, I highly suggest you go do that now because this video won't make as much sense and will be a little bit confusing if you don't preface this one by watching the previous video. So what we have here is, as we discussed previously, the region upstream of the Lac Operon, or the upstream of the beta-galactosidase gene for the Lac Operon. And we already talked about what these three different regions are and what binds to them. Now we're going to talk about what happens when things bind to them. So here first we have the repressor, and the repressor is bound in this scenario. So the repressor is bound, and the RNA polymerase with the sigma factor is actually not going to be able to transcribe the gene because, again, it can't get past that repressor. The repressor is bound tightly, and it's not going to stop binding just because the RNA polymerase is there. That's actually good because it conserves resources. Well, why is that good? Well, that's because the repressor, if you recall from the previous video, is only active when lactose is absent. So if lactose is absent, then we don't need to produce beta-galactosidase, which is an enzyme that breaks down lactose. So you don't want to break down lactose if you don't have lactose, right? It doesn't make sense. So that would just be a waste of transcription and translation. So as I said, it's actually good to have that repressor in place at the appropriate time. Now, when lactose is present, as we discussed in the previous video, lactose is a disaccharide or a carbohydrate that is made up of two molecules. These are both glucose molecules. I think I had L's in here just to stand for lactose. The whole thing is one lactose molecule. And we said that this lactose molecule will come and it'll bind to the repressor, and it changes the shape of the repressor. The repressor goes into an alternate conformation. Here we indicated that with a rounded bottom, and it can no longer bind to the DNA. So when this happens, then the repressor is inactive. So again, I'm going to draw this kind of bouncy arrow. So the repressor is inactive. It can't bind to the DNA. And so basically, it's not going to be there to stop the RNA polymerase. So the RNA polymerase, if it binds at the promoter, could transcribe. It's not going to be super great at transcribing on its own. Now, what do I mean by on its own? What else would it need? Well, that's the other component that we talked about previously, the cap binding protein and the cyclic AMP can be bound on the other side over here. So the cap binding protein, when it is bound to the CAMP, or cyclic AMP, that indicates that energy levels are low. So this structure here, this molecule, can help our RNA polymerase to bind to the promoter better. It stabilizes it, helps it remain on that DNA, and then once the RNA polymerase is stabilized, then it's going to move forward and transcribe. This interaction is just temporary. It allows, again, this structure here to stabilize the RNA polymerase, just like, if you're helping a friend if you're ice skating and you're trying to help a friend, you don't hold on to them the whole time you're ice skating. That would be really cumbersome. You might help them get up and then steady them and then let them go. And so that's the situation here. We have a steadying or assistance of the RNA polymerase, and then the two are no longer going to associate. Okay, so the next thing here is that you can start to make combinations of what is present in the cell. So if the cell has lactose present, so we have our lactose, I feel like I'm drawing this like larger and larger every time. So we have lactose, which is our disaccharide, and it's present. And so that means that we're bound to the repressor. The repressor is not active, okay? But we do not have the cap binding protein present because actually there's lots of glucose in the cell as well. So in that case, we have plenty of energy in the cell. So this is some glucose that I'm just drawing over here. And so we don't have low energy. We don't have high levels of cyclic AMP. Instead, we have high levels of ATP. And that's fine. That means that we probably don't need to start breaking down this lactose for energy. And in that case, we do not have anything bound here. And again, that's fine. So we might get RNA polymerase doing some transcription, just not a lot of transcription. Alternatively, we might have the cell very low on energy, which means that we will have our cap binding protein bound here with our cyclic AMP. Okay, so this is again because the cell is low on energy. Did I say protein before? I'm not sure. Cell is low on energy, low ATP. We have lots of cyclic AMP floating around, but if there's no lactose present, there's still no point in using the resources to transcribe this gene. So if there's no lactase present, lactose, if there's none of that carbohydrate present, then we still are going to have this repressor in place because there's no point in producing beta-galactosidase, transcribing and building DNA, RNA is going to take energy. We don't want to use energy to make an enzyme that breaks down something that's not there, right? Especially when we have low energy. So in this scenario, we're not going to have the RNA polymerase transcribe. Does that make sense? Okay, so I think that covers all of the situations that we might come across. Sorry if the picture is a little bit delayed compared to what I'm saying. I'm not sure why that's going on, but if you have any questions, of course, don't hesitate to contact me.